This is the revision video about complex numbers and in particular Demas theorem for the FM4 unit of the WJEC Further Mathematics specification. So the key skills we've got to make sure we understand are Demas theorem and how it can be used in both trigonometry and to find sums of series. And we also need to understand the fact that the complex number cos theta plus I sine theta can be written in exponential form as e to the I theta. So, first of all, power series work that you'll also have looked at during the course of this unit will have explained why e to the I theta is exactly the same thing as cos theta plus I sine theta. And that gives us three different ways of writing the complex number whose modulus is r and whose argument is theta. We can write it in polar coordinate format, if you like, as simply r theta. Or we can say that z is equal to r cos theta plus I sine theta. Or we can say that z is equal to r e to the I theta. And it is well worth your while being able to work with all three of these formats. Demas theorem says that if z is equal to cos theta plus I sine theta and n is a positive integer, then z to the n is equal to cos theta plus I sine theta to the power n, which is cos n theta plus I sine n theta. And Demas theorem can be proved using proof by induction, and this is a proof that you are expected to be able to produce. So Demas theorem can be used for several different things. First of all, complex number arithmetic. It can be used to find integer powers of complex numbers. So if we've got mod w equals r and argw equals theta, then w to the n is r to the n cos n theta plus I sine n theta, or if we like, r to the n e to the I n theta. We can also find the nth roots of w, and there are going to be n different nth roots of a complex number w, and these roots are given by r to the 1 over n, and then we've got cos theta plus 2k pi over n plus I sine theta plus 2k pi over n, where k can take the values 0, 1, 2, 3 up to n minus 1. Demas theorem can be used to obtain trigonometric results, in particular results for multiple angles such as cos phi theta equals 16 cos to the phi theta minus 20 cos cube theta plus 5 cos theta. And we'll see some examples of this later in this video. If we use Demas theorem for z equals cos theta plus I sine theta, then we can show that z to the n plus z to the minus n is 2 cos n theta, and z to the n minus z to the minus n is 2 I sine n theta. And using that, we can deduce other trigonometric identities. And again, we shall see some examples of these later in this video. Okay, so for our first example, we have z is equal to minus 1 plus I. We have to find the modulus of an argument of z. We have to find the cube roots of z. And we have to find the smallest positive integer n for which z to the n is a positive real number. So, to find the modulus and argument of z, it's always a good idea to start by having a quick sketch showing the complex number z on the Argand diagram. So there we are. Modulus of z is going to be the square root of the real part squared plus the imaginary part squared. So in this case, we've got the modulus of z is the square root of minus 1 squared plus 1 squared, which is root 2. From the diagram, we can see that the triangle that we've got drawn there is an isosceles right-angled triangle. So the angle theta must be 45 degrees, or pi by 4, which means that the argument of z, which is the angle from the positive real axis round to z, must be 180 minus theta, or 135 degrees, or pi, take away pi by 4, which is 3 pi by 4. So, if we decide that we're going to use radians for the rest of this question, we've got the modulus of z is root 2, and the argument of z in radians is 3 pi by 4. For the second part of the question, we have to find the 3 cube roots of z in the form x plus iy, giving x and y correct to 3 decimal places. We know that the modulus of z is root 2, the argument of z is 3 pi by 4, so we have got z is 2 to the half times by e to the I 3 pi by 4. So the cube roots of z are going to be 2 to the half to the third times by e to the I 3 pi by 4 plus 2k pi divided by 3, where k can take the values 0, 1 or 2. If we start off with k equals 0, that gives me 2 to the 1/6 times e to the I pi by 4, which is the same thing as 2 to the 6th times cos pi by 4 plus I sin pi by 4, which we can calculate as 0.794 plus 0.794i. For the second root, we need to put k equals 1, which gives me the second root is 2 to the 1/6 times by e to the I 11 pi by 12. Now that 11 pi by 12 comes from 3 pi by 4 plus 1 lot of 2 pi, all divided by 3. So that's the same thing as 2 to the 1/6 times by cos of 11 pi by 12 plus I sin 11 pi by 12, which calculates through to minus 1.084 plus 0.291i. And for the third root, we need to substitute k equals 2, and that will give me 2 to the 1/6 times by e to the I 19 pi by 12. So that's 2 to the 1/6 times cos 19 pi by 12 plus I sin 19 pi by 12. And the calculator again, this stage gives us 0.291 minus 1.084i. And the final part of the question says we have to find the smallest positive integer n for which z to the n is a positive real number. Well, we know that z is 2 to the half times e to the I 3 pi by 4. So z to the n is 2 to the half times by e to the I 3 pi by 4 all to the power n, which is 2 to the n over 2 e to the I 3 pi by 4 times by n. So we can deduce that the argument of z to the n is 3 pi by 4 times n. Now, z to the n will be a positive real number if argument of z to the n is a multiple of 2 pi. So, we know the argument of z to the n is 3 pi by 4 times n, which is the same thing as 2 pi times 3n over 8. So if this is going to be a multiple of 2 pi, we need 3n over 8 to be a positive integer. And the smallest value of n, the smallest integer value of n, such that 3n over 8 is a whole number, is n equals 8. Moving on to our next example, we have to write down Demas theorem for n equals 5, and hence show that for sine theta not equal to 0, sine phi theta divided by sine theta is equal to a cos to the 4 theta plus b cos squared theta plus c. And then we have to use that to determine the limiting value of sine phi theta divided by sine theta as theta tends to 0. So Demas theorem for n equals 5 tells me that cos theta plus I sine theta to the power 5 is equal to cos phi theta plus I sine phi theta. Now we're going to introduce a shorthand for this. Let's write C for cos theta and S for sine theta. So we've got C plus IS to the power 5 equals cos phi theta plus I sine phi theta. We can use the binomial expansion now to expand C plus IS to the power 5. So binomial expansion will give me C to the 5 plus 5 lots of C to the 4 IS plus 10 lots of C cubed IS squared plus 10 lots of C squared IS cubed plus 5 lots of C times IS to the power 4 plus IS to the power 5 must equal cos phi theta plus I sine phi theta. Now we need to work through this carefully. So the first term is just C to the, on the left hand side is just C to the 5. The second term on the left hand side is going to be 5I C to the 4S. The third term on the left hand side is going to be 10 C cubed I squared, which is minus 1, times by S squared. So that gives me minus 10 C cubed S squared. The fourth term on the right hand side is going to be 10 C squared I cubed, which is the same thing as minus I, times by S cubed. So that gives me minus 10 I C squared S cubed. The fifth term on the right hand side is 5C I to the 4, which is 1, S to the 4. So that's just plus 5C S to the 4. And the final term on the left hand side is I to the 5, which is I times by s to the 5. So that is just I s to the power 5. So we now know that c to the 5 plus 5c to the 4 si minus 10c cubed s squared minus 10c squared s cubed I plus 5c s to the power 4 plus s to the 5 I is equal to cos phi theta plus I sin phi theta. Now what we want to obtain is sin phi theta. And sin phi theta is the imaginary part of the right hand side. So we're going to look at the imaginary part of the left hand side. So the imaginary terms on the left hand side are 5c to the 4 si minus 10c squared s cubed I plus s to the 5 I. And the imaginary terms on the left hand side must equal the imaginary terms on the right hand side, which is just I times sin phi theta. So we have 5c to the 4 s minus 10c squared s cubed plus s to the 5 must equal sin phi theta. So, dividing through now by sin theta, because we've been told that sin theta is not equal to naught, and that's perfectly allowable. So we've got sin phi theta divided by sin theta is going to be 5c to the 4 minus 10c squared s squared plus s to the 4. Not quite there yet, because we've still got s squared and s to the 4 there, and the target that we're aiming for in the question is that sin phi theta over sin theta should be a cos to the 4 theta plus b cos squared theta plus c. So we've still got a little bit more work to do. What we need to remember at this stage is that we know that cos squared theta plus sin squared theta is always equal to 1. So therefore sin squared theta is 1 minus cos squared theta, or s squared equals 1 minus c squared, and sin to the 4 theta is the same thing as sin squared theta squared, so that's 1 minus cos squared theta squared. So we can replace the s squared by 1 minus c squared, and we can replace the s to the 4 by 1 minus c squared squared. So we've got sin phi theta over sin theta equals 5c to the 4 minus 10c squared times 1 minus c squared plus 1 minus c squared squared. So we've got some expansion to do now. First of all, 1 minus c squared squared is 1 minus 2c squared plus c to the 4. Expand and simplify. We'll find that we have, first of all, 5c4 minus 10c squared times minus c squared gives me another 10c to the 4, plus another c to the 4 is 16c to the 4. Looking at the c squared terms, we've got minus 10c squared minus another 2c squared gives me minus 12c squared, and then the constant term is 1. So we've got sin phi theta divided by sin theta is 16 cos theta to the power 4 minus 12 cos theta squared, add 1, which is the required expression where a equals 16, b equals minus 12, and c equals 1. Now we want to consider what happens as theta tends to 0. Well, as theta tends to 0, we know that cos theta tends to 1. So therefore, 16 cos to the 4 theta minus 12 cos squared theta add 1 is going to get closer and closer to 16, take away 12, add 1, which is equal to 5. Right, as our final example, we are told that z equals cos theta plus I sin theta. We have to show that z to the n minus 1 over z to the n is equal to 2I sin n theta. We have to obtain a similar expression for z to the n plus 1 over z to the n. And then finally, by expanding z minus 1 over z to the power 4, we have to show that sine to the 4 theta can be written as a cos 4 theta plus b cos 2 theta plus c, where a, b and c are constants. So, if we know that z is cos theta plus I sin theta, then Demas theorem tells me that z to the n is cos n theta plus I sin n theta. Moreover, z to the minus n, or 1 over z to the n, is the same thing as 1 over cos n theta plus I sin n theta. And we know how to divide 1 by a complex number. We need to multiply the top by the complex conjugate of the denominator and multiply the bottom by the complex conjugate of the denominator. So the top is just cos n theta minus I sin n theta. The bottom is cos n theta plus I sin n theta times cos n theta minus I sin n theta. So that gives me cos n theta minus I sin n theta over cos squared n theta plus sin squared n theta. But the bottom is cos squared n theta plus sin squared n theta, which is always going to equal 1. So we've got 1 over z to the n is equal to cos n theta minus I sin n theta. So we've got these two expressions. We've got, first of all, z to the n is cos n theta plus I sin n theta. We've got 1 over z to the n is cos n theta minus I sin n theta. If we subtract number 2 from number 1, we get z to the n minus 1 over z to the n is 2I sin n theta, which is exactly the expression we were asked to prove. And if we add equation 1 and equation 2, we get z to the n plus 1 over z to the n is 2 cos n theta. Moving on to part B then, we have to expand z minus 1 over z to the power 4. To show that sine to the 4 theta can be written as a cos 4 theta plus b cos 2 theta plus c. Well, the first thing we've got to remember is that we know that z to the n minus 1 over z to the n is 2I sin n theta, if z is cos theta plus I sin theta. So putting n equals 1, we know that z minus 1 over z is equal to 2I sin theta. So we know that z minus 1 over z to the power 4 is going to be the same thing as 2I sin theta to the power 4. Now we'll expand, first of all, the left-hand side using the binomial expansion. So that's going to give me z to the 4 plus 4 lots of z cubed times minus 1 over z plus 6 lots of z squared times minus 1 over z squared plus 4 lots of z times minus 1 over z cubed plus 1 lot of minus 1 over z to the power 4. So that's just my binomial expansion. On the right hand side, I've got 2i sine theta to the power 4, which is 2 to the 4, times by I to the 4, which is 1, times by sine theta to the power 4. So we've got 2 to the 4 is 16, I to the 4 is 1, times by sine theta to the power 4. So that's 16 sine to the 4 theta. Tidying up the left hand side, we get z to the 4 minus 4z squared plus 6 minus 4 over z plus 1 over z to the 4. Just take care with all the signs there. So we've got z to the 4 minus 4z squared plus 6 minus 4 over z squared plus 1 over z to the 4 is 16 sine to the 4 theta. If we now pair up the z to the 4 and the 1 over z to the 4 and the minus 4z squared and the minus 4 over z squared, we've got z to the 4 plus 1 over z to the 4 minus 4 lots of z squared plus 1 over z squared plus 6 equals 16 sine to the 4 theta. But from the first part of the question, we know that z to the 4 plus 1 over z to the 4 is 2 cos 4 theta. And we also know that z squared plus 1 over z squared is going to be 2 cos 2 theta. So the left hand side can now be written as 2 lots of cos 4 theta minus 4 lots of 2 cos 2 theta plus 6 equals 16 sine to the 4 theta. And if we divide through by 16, that now gives me 1/8 cos 4 theta minus a half cos 2 theta plus 3/8 is equal to sine to the 4 theta, which is exactly what we want, with A equals 1/8, B equals minus a half, and C equals 3/8.